Okay, so I want to talk a little bit about section 2.3. In section 2.2, we talked about what an invertible matrix is and how to find an invertible matrix. And in section 2.3, we go into a little more detail about properties of invertible matrices. Okay, so section 2.3 is called characterizations of invertible matrices. And there's a theorem I want to show you called the invertible matrix theorem. Okay, let me go here. Here it is. Look at that theorem 8, the invertible matrix theorem. Sorry. Look at that lovely theorem. Well, so now you see, Mikhail, this theorem, it is a long theorem, but when you do enough practice problems, a lot of these parts of the theorem are going to make sense. The invertible matrix theorem applies in section 2.3 for a square matrix. Remember, you can't have an inverse of a non-square matrix. And it says in the theorem, the following statements are all equivalent. Okay, they're all equivalent. This means that for a given matrix A, the statements are either all true or all false. Okay, so let's take a look at statements A and C. So statement A says that if A is an invertible matrix, then the matrix A has n pivot positions. But if the matrix A is not an invertible matrix, then the matrix A would not have n pivot positions. So this relates to the example we just saw from section 2.2. Let me go back to that practice problem that we just looked at. Okay, let me go look at it here. Hold on, everybody. Yeah, this will be fine. So there is a matrix A. The matrix with first row 1, -2, -1, second row -1, 5, 6, third row 5, -4, 5. We do row operations on the matrix A, and we end up with the matrix on the bottom that has 3 zeros on the bottom row. How many pivot positions does the matrix A have? That's right, Bellin, 2. So this goes with the practice problem at the end of section 2.2, the second practice problem. So because the matrix A does not have 3 pivot positions, this means the matrix A is not invertible. You see? So we're utilizing here, that is an example of theorem 8 with parts A and C. So yes, if A is invertible, A has 3 pivot. If A is a 3 by 3 matrix and A is invertible, A will have 3 pivot positions by the fact that A implies C and C implies A. But if A is not invertible, then A does not have 3 pivot positions. You see, the statements are either all true or all false. Okay, so that's an example of how you can apply this theorem. And what we're going to be doing is we're going to be looking at some of the results of this theorem, this invertible matrix theorem, as part of our next class, part of Wednesday's class. But let's take a look at maybe an example or two here. Okay, hold on here. Yeah, example 1. Okay, and this actually relates to a question that Mikhail had. How do you determine if a matrix is invertible? Well, of course, we know how to do it using the algorithm, but, well, here's a matrix A, and they row reduce the matrix A, and the resulting matrix, so they're leaving out some steps, right? They're leaving out some steps here, but the resulting matrix A, when you do the resulting matrix, the matrix A is equivalent to that highlighted matrix there. How many pivot positions are there in the highlighted matrix? How many are there? How many pivots do you see? What are the pivots? In the highlighted matrix? That's right, Mikhail. But I want to make sure everybody's okay with this. Do you see that the pivots are 1, 1, 3? Marcellus sees that. Okay. 3 by 3 matrix with 3 pivots. That means by the invertible matrix theorem, A is invertible. Okay. So that's an example of how to use the invertible matrix theorem. Okay. Now let's look at another thing on the invertible matrix theorem here. Let's look at another. So if I hold on. Let me just take this off. Let's try to relate properties A and G, statements A and G of the invertible matrix theorem. It says if A is an invertible matrix, then the equation AX equals B has at least one solution for every vector B in Rn. Let's see if we can prove that real quick. Okay, why would that be true? Well, let's take a look. So here you have A times X equals the vector B. A is an n by n. Let me start it again here. A times the vector X equals the vector B. A is an n by n matrix, a square matrix. X is an n by 1. The vector B has to be an n by 1. Now, if A inverse exists, that means A is invertible. What can we do? Well, we can take our matrix equation and we can multiply the left side of both sides of the equation by A inverse. But what is A inverse times A? What is the A inverse times the matrix A equal? When you multiply a matrix A by its inverse, what do you get? The identity. That's right, Bella. The identity. So on the left side, that's right. All right, Bella. So on the left side now, you have the identity times a vector x equals A inverse times B. Well, what is the identity times the vector x? Equal to. What is that's right, Bella. It equals the vector x. Thank you. So the vector x equals A inverse times the vector B. Okay, so this means then, so AX equals B has a solution, X. Okay, so this is like in the invertible matrix theorem, this is the statement A, and that implies the statement G. Okay, so we basically, on the IMT, the invertible matrix theorem, we abbreviate invertible matrix theorem with INT. This shows that A implies G. Statement A implies statement G. Okay, so we go back there. Statement A implies statement G. See that? So the invertible matrix theorem, when you look at it, it seems a little bit, oh wow, you know, that's, how many are like, this is the biggest theorem I've ever seen in my life in math? How many of you are like, this is the longest theorem I've ever seen yet? What do you think, Jacob? Is that like a long theorem for you? Okay, David thinks it's pretty long. Jacob thinks, well, okay, Jacob, I hear you there. Okay. All right. So, you know, but if we just sort of, you know, in the homework for section 2.3, and I've not made that available yet, we need to do a little more on 2.3. But the problems that you'll see are to reinforce this invertible matrix theorem, and you'll see that. Okay, are there any questions? We'll continue section 2.3. We'll talk more about it on Wednesday. Are there any questions before I stop the recording? Okay, you're welcome, Jonathan. All right, let me go ahead and stop the recording here.